So in chemistry, we have two types of compounds. We have ionic compounds and covalent compounds. Ionic compounds are made up of ions, whereas covalent compounds are made up of molecules. And later on in uh, chapter 4, we talk about covalent compounds, naming covalent compounds, and drawing covalent compounds. So we're just going to strictly reference ions. And so ions are made up of charged species, which we call cations and anions. And so what we mean by charged species is we mean that the number of protons and electrons is not the same. So for most neutral elements, or for all neutral elements, we have the same number of protons and electrons. But when we form ions, which are charged species, they're no longer equal to each other. So usually the electrons is either more, as in anions, or less, as in cations. And so we have to have a combination of both cations and anions, which are oppositely charged, to have an ionic compound. So if you don't have an anion, you can't have an ionic compound. If you don't have a cation, you can't have an ionic compound. So you have to have both of these cations, and it's referred to as cations, not cations, but cations and anions together in order to have a ionic compound, because they have opposite charges which attract to one another. And so there are two types, cations and anions. Cations, as we'll see, are positively charged, meaning that the number of protons is greater than the number of electrons. And anions are negatively charged, indicating that the number of electrons is greater than the number of protons. So if a species has less electrons than the protons, it's a cation, which is positive charge. If a species has more electrons than protons, it's an anion, which means it's negatively charged. And so here's an example. We look at sodium, and this goes back to valence electrons. So sodium atom has one valence electron in the 3s1 at the 3s orbital. Now sodium likes to form a cation. So the way you form a cation is you have to lose electrons. So sodium is going to lose its one valence electron to become the sodium cation. And now when it becomes a sodium cation, you see now it has 10 electrons and 11 protons, whereas before, when it was an atom, it had 11 protons and 11 electrons. So since the number of electrons is less than the number of protons, we now have a cation. Now cations, the name of the cation is very easy. It's just the name of the element. So if you have a sodium cation, it's sodium. Calcium cation is calcium. So the names of cations are the same as the name of that element. And again, cations have less electrons than protons. And this is a big thing to remember. Metals always form cations. I'll write that in caps. So if you see a metal, it's always going to be a cation. It's always going to want to lose electrons, and that's because it's more stable when it has fewer electrons than protons. So anytime you see a metal in an ionic compound, you should know that that is a cation. Metals will never gain electrons to form an anion, for example. They always form cations. So now anions, on the other hand, here, as we said, anions have more electrons than protons, and nonmetals form anions. So if you see a nonmetal, it's going to form an anion in an ionic compound. So here we have chlorine, the chlorine atom it has 7 valence electrons, so 3s2, 3p5. As we'll learn in a little while, nonmetals like to obtain 8 valence electrons. And so the way that chlorine can obtain 8 valence electrons is by acquiring another electron. So in the atom, we have the same number of protons and electrons, but when we add an electron to form the chloride anion, now you see the number of electrons is greater than the number of protons. And now chloride has 8 valence electrons, just like the noble gas that it's next to. So let's continue. So now we have cations and anions, and the name for anion is a little bit different than the name of the cation, and we'll talk about naming anions in just a moment. So typically with main group elements and even most transition metals, we like to lose either 1, 2, or 3 electrons to form a cation. And the way we know whether it wants to form, especially with main group elements, it wants to lose 1, 2, or 3 electrons is based on the number of valence electrons it has. So for example, if an element has 2 valence electrons, it's going to want to give up those 2 valence electrons. So it's going to have a +2 charge. So for cations, the way you know the charge is based on the number of valence electrons it has. And it generally likes to give up all of them so that it can become like a noble gas. Whereas anions generally will gain either 1, 2, or 3 electrons. And the reason they gain 1, 2, or 3 electrons is because anions or elements want a total number of 8 valence electrons. And for nonmetals, it's easier for them to gain electrons rather than losing electrons. So if you look at the valence number of nonmetals, you subtract 8 from it, you'll know what the charge of that anion is. So for example, nitrogen has 5 valence electrons. It needs 8. So 5 minus 8 is -3. So nitrogen will have a -3 charge as an anion. Oxygen is 6 valence electrons. It wants 8. So 6 minus 8 is -2. So oxygen likes to have a -2 charge as an anion. And then lastly, fluorine has 7 valence electrons. 7 minus 8, -1. So fluorine likes to have a -1 charge. And that goes for all the elements in those groups. So group 16 or group 15, 5A, 16, 6A, and 17, 7A, all the elements in those groups have the same charge as what we call a monoatomic anion. And what we're adhering to is what's called the octet rule. So the octet rule tells us that elements want 8 electrons in its outer energy shell. And so for metals, it's easier for them to lose electrons to get 8, whereas nonmetals, it's easier for them to gain electrons to get 8. And so that's what they're obeying, is this octet rule. Because all the noble gases, starting with neon down, all have 8 valence electrons and are very stable. And like I've been saying, metals form cations, nonmetals form anions. So in addition to knowing that magical number 8, we can relate the group number to the relative ionic charge for elements in that group. And so again, elements in the same group have similar charge. So whether you're sodium, lithium, potassium, rubidium, any element in that group 1 has a +1 charge. So for the metals, the group number tells you the charge of the cation. So group 1 is +1, group 2 is +2, and group 3, A, is +3. So any element in that group, they all have the same charge for the cation. Now, transition metals are different that we'll talk about in a little bit. Now, for nonmetals, to find the charge, we simply take the group number and subtract it from 8. So we take 8 minus 6, you get 2, but it has to be -2. So nonmetals, anions are always negative charge. So again, for the metals, the cation charge equals the group number. And this is important because when you're writing ionic compounds or naming ionic compounds, you got to know the charges of your ions. So for metals, the main group 1, group 2, and group 3A, the group number tells you the charge. And they're always going to be positive charge. It's never going to change. So group 1 has 1 valence electron and likes to get rid of it. Group 2 has 2 valence electrons. It wants to get rid of all the valence electrons. Again, this is so that it can have 8 valence electrons. And group 3A has 3 valence electrons. It likes to get rid of all of them. So all the elements in group 1 all have a +1 charge. All the elements in group 2 have a +2 charge. And all the elements in group 3 have a +3 charge. Because again, when they have these charges, they now have 8 valence electrons. Now for anions, as we said, it should be the group number -8, so you get a negative number. So for example, group 6A has 6 valence electrons. We need to add 2 electrons so that we get a -2 charge. This should be a -2 here. For group 7A, we have 7 valence electrons. It wants to gain 1 electron to get a -1 charge. And so all elements in group 6A or group 16 have a -2 charge. So oxygen, sulfur, selenium have a -2 charge. All the halogens, fluorine, chlorine, bromine, and iodine have a -1 charge. Same would go for group 5A as well. They want to gain 3 electrons. So group 5A, we're talking about nitrogen, phosphorus, and arsenic. They like to have a -3 charge. The charges are the most important thing to know, because if you don't know the charges, it's going to be very hard to name compounds. This is just an overview. So again, all elements in group 1 have a +1. All elements in group 2 have +2. We'll come back to the transition metals. Group 3A, we're talking about aluminum, gallium. All the elements in that group have a +3. And then you see the common nonmetals have negative charges as well. So these are referred to as monoatomic ions because the ion only has one type of element. So when we get to transition metals and even some what we refer to post-transition metals, these metals can have a variable charge. So things like, or metals like chromium, manganese, iron, cobalt, nickel, copper, gold, mercury, tin, and lead, You notice that they don't have just one ionic charge. For manganese and nickel, it just shows the most common one, but nickel can be a +2 or a +3, and manganese can be anywhere +2, +3, +4, +5. So with metals with variable charges, we have to identify the charge with a Roman numeral. So whenever you see a Roman numeral after a metal, it's telling you the charge of the cation. Now, for zinc, silver, cadmium, these only have one ionic charge. They do not have a variable charge. It means they can only be, silver can only be +1, cadmium can only be +2, and zinc can only be +2. The other transition metals that we're going to talk about can have, and post-transition metals can have variable charges. So again, those are the only three transition metals that has one ionic charge. So you don't have to include a Roman numeral indicating the charge after zinc, silver, or cadmium in an ionic compound, because zinc is always 2+, cadmium is always 2+, and silver is +1. And again, you don't have to memorize these charges. If you know the anion charges that we just went over, you can deduce the cation's charge. So when we're combining cations and anions, we get an ionic compound. What you have to remember is that the overall charge of that ionic compound has to be 0. So for example, if we take calcium cation and a fluorine anion, which is referred to as fluoride. So fluoride is the anion of fluorine. It takes 2 fluoride ions to balance the charge of the calcium cation. You see here calcium is 2+, fluoride is -1. So since fluoride is -1, it takes 2 fluorides to balance 1 calcium. So that's where we get the formula CaF2. And again, the cation is always listed first. The anion is always listed second. If we look at NaCl, sodium has a +1, so we only need 1 chloride to balance the charge, and that's where we get NaCl. Next we have lithium and oxygen. Lithium is a +1, oxygen is a -2, so it takes 2 lithium ions to balance the -2 from oxygen. So that's where we get the formula Li2O. Again, the cation is always listed first, the anion listed second. Next we have barium. It has a +2 charge because it's in group 2. Iodide is -1 because it's in group 7A. So to balance the +2 charge, we need 2 iodide anions. So we get BaI2. Lastly, we have aluminum and oxygen. Aluminum is group 3. It has a +3. Oxygen is -2. So to balance the -2 from oxygen and the +3 from aluminum, the common multiple between 2 and 3 is 6. So we're going to need 2 aluminum ions and 3 oxide ions to balance the charge. And notice at the bottom that all of these add up to 0. So the formula for aluminum and oxide is Al2O3. So this is how we combine ions to form ionic compounds. We take the cation, we take the anion. We have to make sure that we have the correct number of cations and anions so that the overall charge is 0. If it's not, then we have to add more anions or more cations to get the 0 overall charge. So how do we identify which atom or which element is the cation and which is the anion when we're given 2 elements? What we have to remember is that metals, I can't stress this enough, metals form cations and nonmetals form anions. So when you're given two elements, you look for the one that's the metal, such as potassium and calcium. Those are going to form your cations, whereas chlorine and oxygen are nonmetals. Those are going to form your anions. And then we can use the group number to determine the charge of the ion. So we know that potassium is in group 1, it's going to be a +1, whereas calcium is in group 2, it's going to be a +2. Now chlorine or chloride is in group 7A, so it's going to have a -1 charge. Oxygen is in group 16 or 6A, it's going to have a -2 charge. Oops, let me go back. So now we've identified the charge of each ion. So now we have to put, as they say, Humpty Dumpty together. So we got to combine the cation and anion in such a way that when we add the number of cations and anions, their charges balance. So again, this is step 2. We determine how many of each ion we need so that we have an overall charge of 0. One thing to remember is that when the cation and anion have the same charge, meaning that one is a +1, for example, one is a -1, you only need one. Or if one is a +2 and the other is a -2, you only need one of each. So with that said, potassium is a +1, chloride is a -1, so we just need one of each. We get KCl. +1 minus 1 gives us 0. For calcium and oxygen, we have a +2 and a -2. They balance each other out. We get CaO. So we only need one of each ion so that the charge is balanced. So now we're going to look at an example when the cation and anion have different charges, meaning one is, say, a +2, the other one is -3. How do we determine the number of ions for each? So here we have calcium ion and a chloride ion, +2 and -1. So the +2 means that we need 2 chloride ions to balance the +2 charge from the calcium. So in order to balance the charge of the +2, we need 2 chlorides so that the 2 negatives neutralize the +2, because -1 plus -1 plus 2 gives us 0. So since we need 2 chlorides for each calcium ion, the formula becomes CaCl2. Put a 2 right here. So this is a +2, and this is a -1, but we have 2 of them, so it balances the charge. So now we're going to be looking at how we name cations. We're looking at mainly the group 1 through 3A, which is our main group element cations. And so it's very easy to name them. The name of the cation is just the name of the element. So anytime you see a cation and it's a main group cation, all you have to do is give the name of the element. It gives the name of the cation. We'll come back to this. Let me show you how to name anions as well. There we go. And then I'll go back to the previous slide. So for anions, it's a little bit different. For anions, we have to replace the ending of the nonmetal with IDE. And for group 17 elements, it's very easy. You just drop the INE and you replace it with IDE. So bromine, when it's an anion, becomes bromide. Chlorine, when it's an anion, becomes chloride. Fluorine becomes fluoride, and iodine becomes iodide. Now with nitrogen, you have to drop off the OGEN to get nitride. For oxygen, we just retain the OX, so we get oxide. And phosphorus, we drop the ORUS to get phosphide. Sulfur is a little different. Sulfur, we drop the UR to get the sulfide. And these are the main anions that we use. Now for any other anion that's not listed here, all you do is you would drop the ending and replace it with IDE. To give you an example of this, for example, we have selenium, we would drop the IUN and we would get selenide. So selenide is the anion of selenium. So whenever you see IDE at the end of an anion, it means it's a anion with just one type of element. So it's not a mixture of elements. So now knowing this, we're going to look back at those examples. Okay. Oops, that slide's out of place. Go here. So when we're naming ionic compounds with the main group metals, we just need to name the cation and the anion. Bullet 2 is important. We don't have to specify the charge of the cation. That's important with main group metals. And main group metals are your group 1, group 2, and group 3A metals. So we don't have to specify how many ions are of each type are needed to balance the charge. We just write the formula. So it's sodium and fluoride. Since it's a +1 and a -1, this becomes sodium fluoride. So it's just the name of the cation and the anion. That's it. Nothing else you need in the name, because sodium is a group 1 metal. Magnesium and chloride, when we add them together, we get magnesium chloride. Again, just the name of the cation and the anion. And a neat trick to do is what we call the crisscross. So if you take the charge and crisscross with it, we get the number of each other ion. So we need 1 magnesium and 2 chloride. So therefore we just put, since it's 1, it's understood, so we put Cl2, MgCl2. So again, you don't have to include the charge of the ions, and secondly, you don't have to include the charge of the cation in the name. Here we go. So we're going to go through and name the following compounds. So in the first example, we have Al2O3. So again, the cation is always listed first. The anion is always listed second. So our cation is Al. Al is in group 3. So our name of our cation is aluminum. And then the O is the anion. So the anion of oxygen is oxide. So this is aluminum oxide. Next we have K3P. Again, K is the cation, it's potassium, it's group 1. P is the anion, so it's going to be phosphide. So again, we drop the ending of phosphorus and replace it with IDE. Next we have SRS. SR is the cation, it's strontium. The anion is an anion of sulfur, it'll be sulfide. Again, all of these metals are from either group 1, 2, or 3. So we don't have to include the charge of the cation because it only has one charge. Li2O, we have lithium, and then we have oxygen, which is the anion oxide. So this is all you do when naming ionic compounds that just contain cations from either group 1A, 2A, or 3A. So now we're going to talk about how do we name those ions that have, or those elements that have multiple ionic charges. So when these transition metals, such as iron, copper, tin, and lead, for example, can have two different cations, we use two different naming systems. So one way is the systematic naming, where we use a Roman numeral to indicate the charge of the cation. The other way is the common name, in which we use the suffixes OUS for the cation with the smaller charge and IC for the cation with the greater charge. So for example, if we use the systematic naming, Fe2 plus would be iron 2, Fe3 plus would be iron 3. So this is a little bit different than the previous slide where we had cations that just had one ionic charge. Now, if your transition metal has more than two different cations, you can only use the systematic name. Now, for iron, it only has two different cations, so we can use the common name suffixes. So it becomes ferrous and ferric. So OUS indicates the lower charge, IC indicates the higher charge. Now, when you use the common name method, for most of the Latin compounds, you use their Latin name. So for example, iron comes from ferrum, so we use ferrum when writing the common name for the cations. And again, this is only used for those transition metals besides the three I mentioned early on. So you have to include a Roman numeral for the charge, and also include the OUS or IC if it's one of those with only two different cations. So either one is acceptable naming. So this just shows you some of the ones that have systematic naming. Copper is one, of course, iron, mercury, and tin. Also, we have lead. Lead is one as well. It can be Pb. Let me write that better. It can be Pb2 plus. Or it can be Pb plus 4. And so if we use the systematic naming, we would say lead 2. If we use the common naming, we'd have to use the Latin name for lead, which is plumbum. So this would be plumbus, and this would be plumbic. So these are the ones that we use the common ones that we use the common name or systematic name to name the compounds. Notice that for mercury, we don't use its Latin name, we just use mercury. So mercury 1 is called mercurus, mercury 2 is called mercuric ion. For tin, we use stanium, which is the Latin name for tin, so we get stannous and stannic ions as well. So again, this is only reserved for those cations or those elements that have only two ionic charges. And so you may ask, well, how do we write the name? I have to memorize all those ionic charges. You don't. So as long as you know the charge of the anion like for example, chloride is -1, you can determine the charge of the cation. So here we want to give the name of CuCl2. So we need to determine the charge of the cation in order to write the name of the compound. So we have CuCl2. We notice that we have 2 chloride anions. That gives us a total of a -2 charge. So in order for this to be balanced, the copper must have a +2 charge, because -2 + 2 gives us an overall charge of 0. So by knowing the charge of the anion, we can determine the charge of the cation. So you don't have to memorize all the different transition metals. If you just know the charge of the anions, you can determine the charge of the cation. So now that we know the charge of the cation, we can write the name of the cation and the anion. So for the cation, we can do it 2 different ways. Since it's copper, it can be copper 2, or it can be cupric, because +2 is the higher charge of copper. The anion, we add the ending IDE to it, becomes chloride. So the name of this compound is either copper 2 chloride or cupric chloride. Both are acceptable answers. So copper 2, the 2 indicates +2 charge on the copper. Cupric, the ick represents the higher charge of copper, which is the +2. Now here we're going to take the name and write the formula. So we have 10,4 oxide. We want to write the formula for this. So remember that the 4 represents the charge of the metal. Oxide, you should know the charge of the oxide anion. So we have 10 in oxygen or oxide. 10 is a +4. Oxygen is a -2. And so to balance this, we need 2 of the oxides to balance the +4 from the 10. So we get SnO2. Notice here that if you use the crisscross method, you would have gotten SN2O4. Now this is somewhat correct. What you have to remember is that whenever your common multiple between subscripts is not 1, you have to factor out what is the common factor so that you reduce it down to a common multiple of 1. So SN2O4 would be written as SnO2. So this would be the formula of 10,4 oxide. So we're going to look at examples of ionic compounds that contain cations with multiple ionic charges. So first we have Cu3N2. So the cation is copper, and the anion is the anion of nitrogen, which is nitride. But copper is one of those that has 2 ionic charges. So we need to identify what the charge of copper is. Question mark. And so there's 2 different ways you can do this. You can say, hey, I know that nitride is -3. -3 times 2 is -6. So copper has to be a +2 to balance the -6, because 2 times 3 is 6. Another way you can do this, which works most of the time, there are some times when it doesn't, is the reverse crisscross method. And this works most of the time. So what you do is you take the subscript from the anion, it becomes the positive charge of the cation, and you take the subscript of the cation, it becomes the negative charge of the anion. So nitrogen is a -3, copper is a +2. And again, this works the majority of the time for most compounds. So you see copper is a +2. So we can write this compound as copper 2 nitride or cupric nitride. Next we go to 10, or just SnBr2. We have 10, it's the cation, and the anion of bromine is bromide. So again, if we do the reverse crisscross, we can determine the charge of 10, because 10 is one of those that can have a cation of different charges. So we do the reverse crisscross. We see that 10 is a +2, and bromide is a -1. So this will be written as 10,2 bromide or stannous bromide. Because bromide, 10 has a high and a low charge. It only has 2 ionic charges. Now in number, in C, I wrote the wrong element. It should have been an iodine here, not a nitrogen. So it's AuI3. And so again, our cation is gold, and the anion of iodine is iodide. But gold is one of those metals that can have 2 ionic charges. So we need to determine the charge of gold. So if we do the reverse crisscross, we see gold is a +3, and iodide is a -1. So this would be gold 3 iodide or auroric iodide. Because aurorum is the Latin name for gold. So you have to say auroric iodide. Lastly, we get to chromium. So we have Cr2S3. Cr is chromium. S is the anion of sulfur. So it'll be sulfide. Now chromium is one of those metals that has multiple ionic charges. So we need to identify what's the charge of chromium. So we do the reverse crisscross. We see chromium is a +3. Sulfide is a -2. And so this would be chromium 3 sulfide. Now you wouldn't use the common naming because chromium can have a variety of different ionic charges. So it just uses the systematic naming. I'm just going to show you one example where the reverse crisscross doesn't work. So for example, we have the compound COS. So the cation is cobalt, the anion is sulfide. Now if you do the reverse crisscross, this is going to tell you that cobalt is a +1 and sulfide is a -1. But that can't be true because we just told you that sulfide is a -2. So if sulfide is a -2, cobalt has to be a +2. So this would be cobalt to sulfide. So this is one occurrence where the reverse crisscross doesn't work.